Welcome to Momentum, Knowledge in Motion, and thank you for joining us for episode 4. Today, we're diving into a fascinating topic that's been gaining traction in the field of artificial intelligence: measuring hallucination in large language model outputs. Let's kick things off with our first paper. The paper, titled Hallucination Detection Using Multi-View Attention Features, is authored by Yuya Agasa from the University of Osaka and Yuki Ares from the Institute of Science in Tokyo, Japan. This research introduces an innovative method for detecting hallucinations in outputs generated by large language models, focusing on the analysis of multi-view attention features. At the heart of this study is the extraction of token-level attention metrics, which include average influence, attention diversity, and reference breadth. These metrics are crucial for classifying spans of text that may be hallucinated, essentially, text that is fabricated or inaccurate. The experimental results are promising, showing that this new method outperforms existing techniques, especially in tasks like data-to-text generation and summarization. The researchers utilize 3 key features to capture attention irregularities: average incoming attention entropy, and outgoing attention entropy. By employing a transformer encoder for token-level classification, they can efficiently pinpoint hallucinations, which significantly enhances the reliability of language model outputs across various applications. Diving deeper, the study emphasizes the importance of attention weights and their role in context dependency within transformer models. It proposes an adjusted attention matrix that improves hallucination detection by allowing the model to prioritize more informative tokens, thus refining classification accuracy. A critical component of this research is the RAG truth dataset, which consists of 18,000 annotated responses across 3 scenarios: question answering, data-to-text generation, and summarization. This dataset is meticulously designed to facilitate robust evaluation through token-level metrics, which enhances the effectiveness of the proposed method in diverse applications. The results are impressive, with the proposed method achieving the highest F1 scores in data-to-text and summarization tasks and showing higher recall rates in question answering. Notably, using all 3 features consistently outperformed approaches that relied on a single feature. The analysis also reveals that longer contexts improve detection accuracy, particularly in summarization tasks, compared to shorter contexts in question answering. The study categorizes hallucinations into 2 main types: subtle and evident introductions of baseless information, as well as subtle and evident conflicts. The findings indicate that the proposed method excels at identifying evident conflicts, which boosts overall detection accuracy across various applications. When analyzing the performance of the proposed method on the QN2 5-7B instruct model, the researchers found that while their approach outperformed others, the architecture of QN, characterized by fewer layers and attention heads, limited its effectiveness compared to the Llama model. This highlights the critical role that attention mechanism implementations play in hallucination detection, affecting feature extraction and overall model performance. However, the study does acknowledge some limitations. While the proposed method shows effectiveness on the Llama 38B instruct and QN2 5-7B instruct models, its applicability to other large language models remains untested. Additionally, the current focus is on English, with plans to explore multilingual capabilities in the future. The researchers also aim to investigate unsupervised learning approaches to reduce the costs associated with annotation. To optimize the performance of the transformer encoder, the study employs hyperparameter optimization using the Optina library. Key settings include a learning rate range from 1E5 to 1E3 and a maximum of 150 epochs, with experiments conducted on NVIDIA RTX A6000 GPUs to ensure efficient training and fine-tuning of the proposed method. Now, let's move on to the second paper of this podcast episode. The paper, titled HalluCNOT, Hallucination Detection Through Context and Common Knowledge Verification, developed by AI Mon Labs, introduces an innovative system designed to tackle the issue of hallucinations in large language models, particularly in enterprise settings. At the heart of this research is the HDM2 model, which stands out for its ability to assess both context and common knowledge, making it a powerful tool for ensuring the reliability of AI applications in businesses. The authors have crafted a new taxonomy that categorizes hallucinations into 4 distinct types, which is crucial for effectively detecting these inaccuracies in responses generated by language models. One of the key insights from the paper is the differentiation between 2 types of hallucinations: context-based and common knowledge hallucinations. This distinction is vital because it enhances the HDM2 model's ability to identify when a model is generating misleading or incorrect information. The paper also dives into the nuances of enterprise knowledge versus innocuous statements. Enterprise knowledge refers to proprietary information that is unique to specific organizations, while innocuous statements are those that contribute to the flow of conversation without making factual claims. This careful categorization helps minimize false positives in hallucination detection, ensuring that the system remains practical and useful for real-world enterprise applications. In terms of implementation, the HDM2 model is built on the QN2 5-3B Instruct architecture. It employs a multitask training objective that focuses on context-based detection, alongside a classification head dedicated to common knowledge detection. This modular design not only enhances the model's flexibility, but also ensures it can be tailored to meet various enterprise needs while maintaining low latency and compatibility with existing systems. The system processes queries and optional context documents, delivering judgments on the responses generated by language models. A notable feature is the Common Knowledge Check module, which utilizes intermediate layers of the model to boost performance. This adaptability allows for the integration of specific enterprise knowledge, further refining the accuracy of hallucination detection across different contexts. To enrich the dataset used for training, the authors compiled around 50,000 contextual documents from a variety of sources, including enterprise support tickets and the ESC-AD dataset. They generated diverse questions to enhance the dataset's complexity and employed a 3-class annotation schema for labeling responses, ensuring high-quality annotations that significantly improve the HDM2 model's effectiveness. Performance metrics reveal that HDM2 outperforms several baseline models on the RAG-Truth dataset, achieving impressive precision and recall rates. Remarkably, it does so with fewer parameters, showcasing its efficiency in detecting both response-level and common knowledge hallucinations, which reinforces its suitability for enterprise applications. The paper also touches on ongoing research initiatives, such as the Hallucinations Leaderboard, aimed at standardizing how hallucinations in language models are measured. This effort complements the HDM2 model by providing benchmarks for evaluating hallucination detection systems, fostering collaboration and innovation in the realm of AI reliability. Lastly, the authors emphasize the importance of integrating external knowledge and automated feedback mechanisms to further enhance hallucination detection. By employing retrieval-augmented techniques, the system can improve its contextual understanding, thereby reducing inaccuracies. This approach aligns with broader research goals focused on refining the reliability of language models and advancing AI applications in enterprise environments. Next up, we have our third paper to discuss. The paper titled HalluCNT: Measuring Distribution Shifts Towards Hallucination Detection in LLMs comes from a collaborative research effort involving institutions like the Electronics and Communication Sciences unit at the Indian Statistical Institute in Kolkata, Netaji Subhash Engineering College, and East China Normal University in China. At the heart of this research is HalluCNT, a groundbreaking method designed to detect hallucinations in large language models, or LLMs. Now, what are hallucinations in this context? They're essentially errors that these models make, similar to cognitive mistakes humans might have, where the output may sound coherent but lacks factual accuracy. The paper dives into advancements in reasoning techniques that enhance LLM performance, particularly focusing on methods like chain of thought, or COT, and its zero-shot variance. These techniques help models tackle complex tasks more effectively. The authors also highlight methodologies such as plan and solve and hint of thought prompting, which not only improve logical reasoning, but also help reduce hallucinations. Now, let's break down how HalluCNT works. The methodology involves extracting features from the internal layers of LLMs to analyze distribution shifts and cosine similarities. By identifying hallucinations through probabilistic features and membership functions, HalluCNT critiques existing methods for their shortcomings, particularly in addressing cascading hallucinations. HalluCNT's framework is quite sophisticated. It uses a membership assignment function to evaluate hallucination scores by mapping generated text back to the original prompts. This involves incorporating probabilistic features derived from token-level predictions, which significantly boosts detection accuracy. The analysis of distribution shifts across layers reveals critical insights into how hallucinations form within LLMs. The paper also introduces additional features for HalluCNT, such as minimum token probability, maximum probability spread, and mean gradient. These features enhance the detection process by analyzing token confidence levels and transitions. A membership function synthesizes these signals, allowing for precise segmentation of factual versus hallucinated content across various question-answering datasets, which validates the effectiveness of HalluCNT. Quantitative evaluations in the paper showcase HalluCNT's superior performance on the HalluVAL benchmark, with impressive accuracy improvements over existing methods, like a 22% gain in knowledge-grounded dialogue tasks. This ability to track internal feature representations significantly enhances hallucination detection across different datasets, further validating the innovative approach of HalluCNT. Interestingly, the evaluation extends to summarization tasks, where HalluCNT shows comparable performance in hallucination detection to existing methods, even if it has slightly lower accuracy and F1 score in QA tasks. The authors emphasize that HalluCNT's focus on internal dynamics provides more reliable signals of hallucination, which helps in understanding factual inconsistencies and their propagation in generated outputs. The paper employs a dual-perspective analysis to assess HalluCNT's effectiveness, utilizing feature importance through perturbation and generalization across multiple QA datasets. The results indicate robust performance with minimal degradation in AUC-ROC scores, particularly excelling with a window size of 2, which optimizes detection while balancing computational efficiency. Finally, the authors underscore the importance of assessing the internal representations of LLMs to enhance hallucination detection. They suggest future research directions, including the implementation of explicit regularization during training and the integration of HalluCNT with reinforcement learning for automated hallucination feedback. This could pave the way for more effective strategies to mitigate hallucinations in LLMs. The paper also references related works that delve into uncertainty quantification and knowledge representation in LLMs, such as Truthful QA and BLEURT. These studies contribute to a broader understanding of how models can better express uncertainty and improve factual accuracy, aligning perfectly with HalluCNT's goals of enhancing hallucination detection and overall model reliability across various applications. As we continue, let's explore the insights from our fourth paper. The paper titled Possibility of Automated Hallucination Detection in Large Language Models comes from a research group at Yale University, featuring authors Amin Karbasi, John Sues, Omar Montasser, and Grigoris Velikas. This study dives into the challenging world of automated hallucination detection in large language models, or LLMs. So, what exactly does that mean? Well, hallucinations in this context refer to instances where these models generate outputs that are factually incorrect or nonsensical. The researchers found that detecting these hallucinations is closely tied to the complex task of language identification, which is notoriously difficult. However, there's a silver lining. The study reveals that when you incorporate expert-labeled feedback, essentially guidance from knowledgeable humans, this daunting task becomes much more manageable. This highlights the critical role of reinforcement learning with human feedback in improving detection capabilities across various language collections. The researchers emphasize that without external signals or reliable training data, automated detection remains a tough nut to crack. They argue that to enhance the efficacy of detection, it's crucial to have a solid foundation of both positive examples, where the model performs well, and explicitly labeled negative examples, where it fails. This aligns with both classical theories and modern approaches in AI, reinforcing the idea that expert feedback is invaluable. The study also provides compelling evidence of the inherent tendencies of LLMs to hallucinate, pointing out that the way these models process functions is key to understanding their reasoning. They stress the need for structured external feedback to help mitigate these hallucinations, echoing findings from previous research. To tackle the complexities of hallucination detection, the authors introduce a formal model that sets up a game between a learner and an adversary. In this setup, the learner queries whether a target set is hallucinating based on a chosen language. This framework allows for a rigorous analysis of detection capabilities, emphasizing the importance of structured feedback for effective learning. One of the standout points in the study is the reference to Theorem 2.1, which indicates that no effective detection algorithm can exist for certain language collections. This complexity suggests that real-world applications may face even greater challenges due to the nuanced inaccuracies that can arise in generated statements. Interestingly, the study draws parallels between language identification, generation, and hallucination detection, noting that algorithms often lack feedback on their guesses, similar to the pre-training phase of LLMs. The researchers assert that detecting hallucinations is as challenging as identifying languages, which further underscores the need for additional information, particularly negative examples, to boost detection capabilities. The findings culminate in Theorem 2.3, which states that for any countable language collection, there exists an algorithm that can detect hallucinations in the limit when provided with negative examples. This connection between language identification and hallucination detection enriches the theoretical framework for automated detection methodologies. To put their theories into practice, the authors propose an algorithm that combines an identification algorithm with a membership oracle. This systematic approach evaluates language collections by iterating through inputs to determine if the LLM output is hallucinating. Their method reinforces the idea that effective detection relies on structured identification processes and the intricate relationship between hallucination detection and language identification. Finally, the study delves into the intricacies of language identification, arguing that a consistency-based approach alone isn't enough for effective detection. They suggest a complementary strategy that integrates hallucination detection algorithms, which helps identify target languages by systematically ruling out non-supersets, ultimately enhancing detection accuracy through coordinated methodologies. Before we proceed, I want to take a moment to address a unique situation we encountered. In this paper, we dive into the fascinating world of AI research, particularly focusing on the transformative potential of large language models, or LLMs, and the challenges they face, such as hallucinations. Hallucinations in AI refer to instances where models generate information that is incorrect or fabricated, which raises significant ethical concerns, especially regarding data privacy and algorithmic bias. To tackle these issues, the authors introduce HalluLens, a new benchmark specifically designed to evaluate LLMs for hallucinations. This benchmark includes a mix of newly created extrinsic tasks and existing intrinsic tasks, with the extrinsic test sets being generated dynamically. The goal here is to create a robust framework that not only assesses the effectiveness of LLMs, but also ensures their responsible and equitable deployment in society. The paper categorizes hallucinations into two main types, extrinsic and intrinsic. It critiques existing frameworks that often confuse hallucination with factuality, which is a crucial distinction. By providing a nuanced categorization, HalluLens enhances our understanding of hallucinations and their implications for responsible AI use. To illustrate the challenges posed by LLM hallucinations, the authors provide examples of both extrinsic and intrinsic types, as well as issues related to factuality. They clarify that while factuality itself isn't a type of hallucination, it is closely tied to the hallucination problem, underscoring the need for comprehensive evaluation methods in AI research. Data-related challenges are also discussed, particularly how unseen or contradictory training data can lead to hallucinations in LLMs. The authors stress the importance of developing benchmarks that are robust against data leakage and ensure real-world applicability and reproducibility. These criteria are vital for fostering transparency and reliability in evaluating LLM performance. HalluLens introduces 3 specific tasks to evaluate extrinsic hallucinations in LLMs. The first, Precise WikiQA, assesses the accuracy of short answers derived from Wikipedia. It dynamically generates 5,000 knowledge-seeking questions, measuring key metrics like false refusal rate, hallucination rate, and correct answer rate. Next, we have the LongWiki task, which evaluates the consistency of long-form content generation against training data. The results show a staggering false refusal rate of 84.89%, with recall at 71.03% and precision at 75.8%. These metrics are derived from prompts based on Wikipedia and are crucial for ensuring that the evaluation pipeline is robust and comprehensive. Finally, the paper analyzes LLM performance across varying question difficulties, categorized by harmonic centrality scores of Wikipedia pages. This analysis informs the LongWiki task and enhances our understanding of how well models can generate accurate long-form content. In summary, HalluLens represents a significant step forward in evaluating LLMs, providing a structured approach to understanding and mitigating hallucinations, which is essential for the responsible deployment of AI technologies. Now, let's get back on track with our 5th paper. The paper titled Evaluating Evaluation Metrics, the Hallucination Detection Mirage, comes from a collaborative research group at the University of Southern California and Apple Inc. This study dives deep into the world of language models, specifically focusing on how we detect hallucinations, those instances when models generate incorrect or nonsensical information. One of the key findings of this research is that many existing hallucination detection metrics fall short when it comes to aligning with human judgment. In simpler terms, the tools we currently use to measure how well a model avoids hallucinations don't always match up with what humans think. This misalignment raises questions about the reliability of these metrics across different datasets. Interestingly, the study highlights the effectiveness of evaluations based on large language models, particularly GPT-4. It suggests that using mode-seeking decoding methods can help reduce hallucinations, which is a promising avenue for improving model performance. However, the researchers found that most existing metrics, aside from GPT-4, do not show consistent alignment with human judgment, and scaling up model sizes doesn't necessarily lead to better detection performance. The research also explored an ensemble of metrics, including K-BERT score and Q2 NLI, which showed potential in improving detection capabilities. Instruction tuning, a technique that refines how models learn from instructions, further enhances these capabilities across various tasks. However, the study points out that there are weak correlations between different metrics, meaning that they often fail to capture hallucinations accurately. Moreover, the study reveals that simply increasing the size of a model doesn't guarantee better detection of hallucinations. In fact, some metrics, like K-BERT score, even performed worse as model sizes increased. This complexity highlights the challenges researchers face in effectively evaluating hallucinations. The limitations of the study are also noteworthy. It primarily focuses on knowledge-grounded dialogue and question-answering tasks, leaving out other important areas of natural language processing, such as machine translation and summarization. This gap presents opportunities for future research to explore these other domains. Recent advancements, such as the GEMMA model, are also mentioned, which delve into fine-tuning techniques for extracting factual knowledge. This indicates a growing interest in enhancing model reliability and tackling hallucination challenges across various applications. Additionally, The study emphasizes the importance of context-aware approaches in research on faithfulness in summarization and conversational reasoning, which could further inform strategies to reduce hallucinations. Finally, the paper utilizes several datasets, including the Begin benchmark and HalluEval, which provide annotated responses for evaluating model performance. This ensures a robust analysis of hallucination metrics across different tasks, with a specific focus on how the GPT-4 evaluator prompt assesses factual consistency while ignoring stylistic differences. We're almost there. Let's delve into our 7th paper. The paper titled Uncertainty Quantification for Language Models, a suite of black box, white box, LLM judge, and ensemble scorers, comes from a research group at CVS Health in Wellesley, MA. It dives into a crucial aspect of working with large language models, or LLMs, specifically focusing on how to detect hallucinations, those instances when these models generate incorrect or nonsensical information. At the heart of this research is a framework that employs uncertainty quantification techniques to enhance the detection of these hallucinations. The authors introduce a tunable ensemble approach that cleverly combines various confidence scores, which significantly boosts the accuracy of detection. To make this framework accessible, they provide a Python toolkit called UCLM, which showcases improved performance over existing methods, especially in high-stakes applications where accuracy is paramount. One of the key insights from the paper is the critique of traditional hallucination detection methods. These often rely on assessments made before deployment, which can be limiting. The proposed framework, however, allows for real-time evaluation, utilizing both black box and white box uncertainty quantification techniques. This flexibility means that practitioners can tailor their detection strategies to fit a variety of applications, ensuring that the framework can evolve with future advancements. The authors also take a critical look at existing text similarity metrics like Rouge and BLEU, pointing out their shortcomings, particularly their sensitivity to variations in phrasing and their failure to capture deeper semantic equivalence. Instead, they propose alternatives such as sentence embedding-based metrics and natural language inference, NLI, models. Innovative ensemble approaches for hallucination detection are also explored in the paper. One notable method is BS detector, which combines observed consistency with self-reflection certainty to improve accuracy. The research shows that using multiple LLM judges to evaluate responses can significantly reduce bias and enhance the reliability of classifications when detecting hallucinations. The paper details several black box uncertainty quantification scores that assess semantic consistency by generating multiple candidate responses from the same prompt. Techniques like exact match rate (EMR) and non-contradiction probability (NCP) are introduced, which contribute to improved detection accuracy. Additionally, a measure called normalized semantic negentropy (NSN) is proposed to gauge response volatility, providing a robust confidence score. To further refine text similarity evaluation, the authors introduce advanced metrics like BERT score and BLURT. BERT score leverages contextualized embeddings to compute precision, recall, and F1 scores, while BLURT is fine-tuned to align closely with human judgments. Normalized cosine similarity, NCS, is also utilized to measure semantic similarity, enhancing the confidence scores even further. The paper presents novel confidence scores, including length normalized token probability, LNTP, and minimum token probability, MTP. LNTP calculates a geometric mean of token probabilities, while MTP identifies the lowest token probability among responses. Additionally, the concept of LLM as a judge scores is introduced, where LLMs classify responses as correct, incorrect, or uncertain, thereby enriching detection strategies. The architecture of the ensemble classifier is elaborated upon, with a focus on parameterizing ensemble weights to improve hallucination detection. Two tuning strategies are proposed: threshold agnostic and threshold-aware optimization. The former maximizes classification performance without a fixed threshold, while the latter optimizes both weights and thresholds simultaneously. In the experimental results section, the authors introduce the filtered accuracy at tau metric, which assesses model accuracy across varying confidence score thresholds. The findings reveal that both white box and black box methods, along with ensemble scorers, significantly enhance LLM accuracy compared to the LLM as a judge approach. And finally, let's wrap up with our last paper for today. The paper titled, "Can LLMs Detect Intrinsic Hallucinations in Paraphrasing and Machine Translation?" comes from a collaborative research group that includes experts from the RISE Research Institutes of Sweden, Uppsala University, KTH Royal Institute of Technology, and the University of Edinburgh. This study dives into a fascinating question. Can large language models, or LLMs, effectively identify intrinsic hallucinations in tasks like paraphrasing and machine translation? The researchers evaluated a variety of open-access LLMs, looking closely at factors such as model size, how the models are tuned with instructions, and how prompts are formulated. What they found was quite intriguing. There's a lot of variability in performance across different models and tasks. Now, let's break down what they mean by hallucinations. The study makes a crucial distinction between two types: faithfulness and factuality. Faithfulness refers to how consistent a paraphrase or translation is with the original source, while factuality is about whether the information is accurate in the real world. The researchers refined the definition of intrinsic hallucinations, clarifying that not every imperfect paraphrase or translation counts as a hallucination. They identified 11 specific categories of hallucinations, such as addition and negation, and created datasets for both paraphrasing and machine translation to facilitate a thorough analysis. In their evaluation, they looked at various model families, including GPT-SW3, to see how well they could detect hallucinations without any fine-tuning. They tested 6 different prompting strategies, each varying in terminology and definitions of hallucination. The NLI models served as efficient baselines, performing particularly well in paraphrasing tasks. The study also examined how different prompt formulations impacted hallucination detection across models. They discovered that while some LLMs, like MetaLlama 370B Instruct, outperformed NLI baselines in machine translation tasks, others, particularly the GPT-SW3 models, face challenges, especially in Swedish. This highlights the complexities involved in cross-lingual scenarios. When it comes to performance consistency, the results showed that model effectiveness in detecting hallucinations tends to be stable across languages, with English often yielding better results. Notably, the EUROLLM17B Instruct model outperformed GPT-SW3 models in Swedish, suggesting that the volume of pre-training data isn't the only factor that matters. Larger models generally performed better, especially those in the Llama 3 family. The researchers also analyzed how the language and formulation of prompts affected model performance. They found that using non-English prompts could influence outcomes in Swedish paraphrasing and translation tasks. The instruction-tuned EUROLLM17B model excelled in specific scenarios, although the overall benefits of instruction tuning across different model families remain inconclusive. One key takeaway is the importance of prompt language in hallucination detection. English prompts typically led to better results, but models like GPT-SW320B Instruct performed well with Swedish prompts, while MetaLlama 370B Instruct shone in French. However, performance stability varied, with some models showing high error rates due to invalid outputs. The study does acknowledge some limitations, such as the vast number of models and prompting methods that make exhaustive testing challenging. They also point out potential class imbalances in hallucination categories and the reliance on developer-provided data for insights into model training. Future research is encouraged to address these gaps and broaden the diversity of languages studied. Lastly, the paper references several important works in the field, including a Finnish paraphrase corpus and recent evaluations of hallucination detection metrics across multilingual generation. The ongoing development of benchmarks and shared tasks is crucial for enhancing our understanding and detection of hallucinations in generative language models. Thank you for joining us in this exploration of hallucination detection in large language models. We hope you found these insights valuable and thought-provoking. Until next time, keep the momentum going in your quest for knowledge.